So I thought I'll start with a joke. So I shared my presentation with my AI and I asked it, I just review it and give me a joke which is relevant to this particular presentation. It came back and it told me, I have seen your presentation. Probably you should start directly jump into it and the audience will consider it a joke. So I'm really hoping that's not the case. I'm Shashank Sharma. I am working with NVIDIA. I'm based in Berlin. Before NVIDIA, I was a part of AMD, before that Intel, so kind of gone through the industry a bit. I focus on the Linux kernel and device drivers, primarily into the GPU and display drivers. Today I'm going to talk about something like, this is an idea, this is a solution, where we are focusing on driving a lot of displays using just a single GPU. Obviously more than what we are doing right now. So let me quickly go into that. If you see the outline of the presentation, I'll talk a bit about the problem first. Then we'll go through the prerequisite that is required to understand the solution. And then if we have the time left, we will talk about the solution as well. So just a bit of introduction about me. I already mentioned a little bit. So I'm working in the industry for last 20 years or so. Mostly kernel device drivers, mostly upstreaming work, and so on. So let's talk about what exactly is the problem. Most of you, and in fact all of you, would have seen a GPU typically. It looks like that at the bottom. And there you can see there are different display outputs. Each of this output port is connected to a display. So even with the most modern, most expensive GPU, you can at a time drive 4 maximum number of displays. If you specifically check on some of the market segments like automotive, infotainment, industrial automation, and few other areas where you need multiple displays, maybe 16, 20 displays within a car infotainment panel, some for mirrors, some for speedometers, some for other different displays, or any other industrial place where we might have to broadcast a lot of, or a particular thing on a lot of displays. There is always a need of driving more number of displays. That means you will need more number of GPUs. The idea here is to understand if we are using the existing infrastructure properly and can we utilize or exploit it a bit more. So we'll see how it goes. First, I would like to explain a bit why can we only drive 4 displays out of the 4 GPU outputs. So it's not just about the port that you are seeing at the end of the display. If you zoom into a GPU design and look at the hardware blocks, this is typically how it looks, where it actually has 4 different display pipelines. Each of these pipelines, it handles a buffer, it does the processing of the pixel, and then finally everything is done, it gives to the HDMI controller, and that is the output that you see coming out of your GPU. So eventually we have total 4 display pipelines, and that's why we can drive only 4 displays at a time. So it's not just about the port, but it is about the hardware pipeline which is available in the GPU. So there are few existing solutions where people have tried to drive more than what is coming out of the GPU. And some of these are, we'll talk about it just in a slide, that what are these solutions and why they are not scalable or why it doesn't work. First one, let's talk about more pipelines. Yeah, so easy, right? Just get more pipelines. You want 16 displays, fabricate 16 pipelines, have a GPU of this big size, very expensive. Nobody can buy it. Perfect. And there's, let's say that if somebody crazily approved also this idea, technically we are not very well utilizing what is already existing. So this is just a overkill. So that's obviously not a scalable thing. There are a few attempts about the FPGA-based pipeline emulation, display pipeline emulation, and I hate that the most. FPGAs are expensive. They are not exactly very efficient. You have to do a lot of work to program them, to interface them with the driver. And after that, you get 1 extra display. Awesome. Instead of 4, I can drive 5. So I don't find it very healthy solution or scalable solution. Then serializer and deserializers are pretty popular in this industry. They also come with a problem of very difficult interface. This is an additional hardware that you have to interface with your GPU via some bus. And then after that, it comes with a different driver. Then you need to synchronize between your GPU driver, display driver, and this driver. So a lot of things. So an idea, it works, but exactly not very scalable again, as per my understanding. So let's talk about the solution, or instead of going into solution, first I want to give some background of what we need to understand the solution. Many of you might already know this, so just bear with me. So this is a typical software infrastructure at a very high level. This is how the software looks like. Um, as you go from top to bottom, you are going closer to the hardware. So if you see the block at the bottom, black block, these are the actual hardwares. So the application is at the highest level. Application doesn't know anything about what hardware it's running underneath, what's the driver, what's the GPU. It doesn't care about it. Application, all it knows that you give me a rendering API or a display API. I'll fill my buffer and I'll send it to you. So if you split the life cycle of a frame buffer or a buffer, you can simply split into two parts. First part in which we are filling the pixels in the buffer. Second part where we are pushing this pixel from the buffer to a display. So the first half is called the rendering part, second half is called the displaying part. Most of you already know this. So this is what the application typically does. It goes via the 3D driver, media driver, fills it pixels using the GPU driver, and once the frame buffer is done, it actually takes the left route and sends the filled pixel frame buffer to a software called Compositor. Compositor is the brain of the whole graphics ecosystem. And in open source, we call it DRM master because it exactly knows what hardware it's running on, what driver it's running on, and how exactly to enable a display pipeline, disable a display pipeline, what processing needs to be done on a pixel. Compositor typically goes to the hardware abstraction layer like libDRM, sends the pixels to the driver, and driver finally sends it to display. So at a very high level, these are some of the blocks which we'll talk about. Now, finally, what is a superbuffer? To understand that how to use superbuffer to drive some displays, what exactly is a superbuffer? Superbuffer is very, very simple. It is a larger buffer created by stitching 4 or 5 or 10 small buffers together. So this is just a pictorial example, you can say. In this example, you can see that there are 4 1920 x 1080 full HD resolution frame buffers, and they are stitched together left. Of course, in the real memory, it won't look like that. This is just for the better understanding. That there is a big 4K buffer or super buffer, 3840 x 2160 pixel, and I have arranged 4 1080p or 1920 x 1080 pixel next to each other inside that 4K buffer. So each of this 1920 x 1080p buffer is a application buffer, and the bigger 3840 x 2160 buffer is actually the super buffer. So we'll use this term further. So I thought you guys should know what exactly is a super buffer. Now the second important term, what is a splitter? So again, this is not a new thing. Most of you would have seen this on a video wall controller kind of in TV showrooms or in airports and different places. This is a very cheap, very dumb hardware. It doesn't know anything. All you have to do is you give one HDMI input here, and it comes with multiple HDMI outputs. You can pre-program it to split the incoming HDMI signal into multiple parts. So you can see in the right side, this is a 99 euro splitter already available in Amazon Germany. So I've just taken the snapshot from there. You can configure the splitter into 1:4 mode, 3:3 mode. It just knows that if you are giving me a big buffer, I know how to split into small buffer and send it to multiple displays. So 1 HDMI in, 4 HDMI out. Okay, so this is another piece of the puzzle. Now, finally, the example scenario which I'll talk about. This is the use case that we're going to talk about. So think about infotainment, automotive cockpit kind of ecosystem. There are 4 applications. One application is weather application, one is the speedometer, another one is the media player, and one is just some wallpaper. Each of these applications, they rendered their buffer somehow using the ecosystem we spoke about, and they prepared their frame 1, frame 2, frame 3, and guess what? Frame 4. And they sent their frame to the GPU compositor. Now, in a very normal working scenario, GPU compositor, how it takes the decision is, I have 4 applications. They are targeted to 4 different output displays. What I'll do is, each of the buffer, I will give it to one pipeline. So buffer 1 goes to pipeline number 1, and that is connected to HDMI 1. Similarly, 2, 3, and 4. Very simple, very no-brainer scenario. This is how the compositor will take each of the buffer and display on the screen. So far, we have spoken about what's the background required and what's the problem. Now let's enter into the solution space. How can we use all this information and drive more than the displays that we are driving right now? Step 1, compose a superbuffer. So the GPU compositor will already know that I am running in an environment that is targeted for a superbuffer composition. And what I'll do is, it will take all these application frames and stitch next to each other into a super frame. So these 4 frames are 1920 cross 1080 each, for example. And the GPU compositor, instead of treating them as individual frames, it's actually stitching them together in a super frame. And instead of having 4 small frames, now we have 1 big frame. And instead of having 4 full HD 1920 cross 1080 frames, we have 1 big 4K frame. That is step 1, where we actually, the compositor knows that we are going through this process. So instead of targeting individual buffers, I should actually target the super buffer. So once the step 1 is done, we will have 1 big buffer. So in the whole idea, this is the only smart step. Everything else was very usual. Yeah, it's kind of expected. In this idea, the compositor is fooling the display driver. Compositor is not telling that you are driving 4 different 1080p individual displays. Instead of that, compositor is telling the display driver that, hey, you are driving 1 4K buffer. So you can see that instead of using all 4 display pipelines, compositor will only flip 1 big 4K buffer to the display pipeline number 1. And instead of setting a pixel clock for 1920 cross 1080, which is around 148 megahertz, it will set a pixel clock which is 4 times of it. That is actually suitable for a 4K display. So something like 594 megahertz. So compositor will create this illusion for the display driver that I'm actually driving 1 super big buffer. And because you are capable of driving that, most of the GPUs can at least drive HDMI 2.0. That means they can support up to 4K 60. So it's very easy for the display driver to drive it. And you can see that the rest of the 3 display pipes, they are now idle. They're not driving anything. And just 1 pipe is actually driving 1 4K buffer. Okay, then you can ask me the question, fine, but eventually what do I do with this super buffer? I don't need a big buffer, I need 4 small buffers. That's where our splitter comes into picture. So the splitter, instead of the pipeline directly delivering it to the output HDMI port, the splitter will come in between. And as I mentioned, it's a dumb hardware, it doesn't care about anything. All it knows is you give me a big buffer, I'll split into 4 buffers and give you to 4 displays. So the input to the splitter would be the output from your display pipe, that is a 4K super buffer. And we'll program it to chop the frame every 1920 cross 1080 pixel. So the first frame will go to HDMI port number 1, second will go to port number 2, third will port 3, and again port 4. If at a high level, if you see, this is like you are zipping a file, sending it to network, and then again unzipping it. Compression and decompression, but with the display driver. So with using 1 pipe, we can actually, and the super buffer composition, we are driving here 4 independent HDMI displays. If I apply the same to the 4 pipes, I can, with 4 splitters, I can actually drive 16 1080p displays. And if you think about it, we are targeting, or at least the problem statement is targeting something like an automotive space. Not every display in automotive, infotainment, or industrial space is very demanding. Sometimes even the smaller displays can be 720p resolution, 640 cross 480 resolution. So you can actually drive 27 720p displays using 1 GPU. And that's where, if you have a good splitter and a good software, this solution is completely transparent to the display driver. You need not to change a single line of code in the display driver. It's all between compositor and the splitter or the hardware vendor. Interesting thing is, in fact, that's a good news for companies like Canonical and Red Hat, because you don't have to bother about the hardware now, or the display driver rather. You can just change something in Mutter, something in VLAN protocol, and that's it, we are done. Now, so the interesting thing is, when I went to my boss, And I told him that, hey, I'm going to present an idea. With that, you will sell less number of GPUs, and we are a GPU company. And I want you to sponsor me for that. He told, okay, yeah, that sounds like a good plan. So the idea here is that sometimes some of the OEMs, particularly in this embedded spaces, they don't consider some of the high-end GPUs because they could be very costly. For one automotive cockpit, if I need 5 or 6 NVIDIA GPUs, the combination becomes very costly. But if there is a particular SKU that using 1 or 2 GPUs, you can drive probably everything, then that opens up new markets for us. So yeah, that's what I'm very glad that my management understood that. So I'm here. So this is a neck-to-neck comparison case, what we were doing earlier versus what we are doing now. So 4 frames, they were going to 4 different display pipelines, and they were driving 4 displays. But now, with a superbuffer, we are driving only 1 pipe, and with a splitter, we are splitting it. So we can drive 4 into 4, 16, or more than that. So these are some numbers, as I mentioned, using a normal GPU, which is available right now, which is probably driving this one. We can drive 16 1080p or 27 720p displays. And it opens up a lot of possibilities in terms of design. So I'll talk about it in the next slide. This is significantly cheaper than having a FPGA, a lot more effective as well. And at least to me, it looks scalable. We'll see when it comes, something like this comes up. So as I mentioned, if you want to do this execution, software changes are very simple, or everything is mostly going into the compositor. Nothing comes into the driver side. Mostly it's transparent. And if you have a good splitter that comes with the active programmable firmware, then even that becomes one-time programming, because in places like automotive or industrial places, display configurations are fixed. You don't expect to hot plug in or plug out a display in a car cockpit. We know that, okay, these are 15 displays, these are the resolutions. So if you know the configuration, it's very easy to write the software for it and just go ahead with that. The only hardware change we need is the splitter, and if you need to program the splitter, maybe a I2C interface or something like that. Now, what kind of designs we can think about it? So let's say that I'm having a GPU that is having 4 pipes. Out of the 4 pipes, I can reserve 2 pipes for very demanding displays. If there could be a case where I need full-fledged automotive or gaming experience, full-fledged media or gaming experience in an automotive as well. So 2 pipes can be reserved for such kind of high dynamic HDR where when the plugging is required, hot plugging is required, something like that. 2 pipes can be reserved for demanding displays, and you are still left with 2 pipes, so you can still drive 8 more displays. So 2 demanding and 8 more, still using 1 GPU, you can drive 10 displays. Think about a case where you have a iGPU plus GPU kind of case, or APU plus GPU kind of case. You can reserve 4 pipes which are coming out of APU, all for demanding displays, and then 4 pipes which are coming out of DGPU, all for superbuffer composition. So it opens up a lot of possibilities, and each of it actually is a design challenge. Also, it opens up markets. And I'm so glad Gerald was not here, because the moment I told we are selling less GPU, he would have been very angry with me. Okay, there are some known limitations with the solution, and one of the challenges that comes is audio. How are you gonna handle audio? So there are some of the smart splitters, they can handle audio. So I was around 6 or 8 months back, I was talking to few independent vendors in Japan, and they mentioned that they can handle the audio as well, split of the audio. In the worst case, you can take audio via 3.5mm jack, and it can be completely parallel channel. So audio is not as big a problem. HDCP and content protection. HDMI spec specifically defines how a HDCP repeater should behave. And if your splitter is behaving as a repeater, you are taken care of. There's no problem there. Irregular refresh rate. So this is something which people ask me a lot of question about, that, okay, what if my one display is 30 FPS, what is 60 FPS or something like that? How would the superbuffer handle that? You can handle that with your design. All your 30 FPS display can go to pipe 1, 60 FPS display can go to pipe 2, 90 FPS can pipe 3, and so on. So if you exactly know how to club your displays, Superbuffer can still handle that. That's still possible. The only limitation that I see is because Superbuffer is a combination of the smaller buffers, the modification or the transformation using display engine is not possible. You have to always use the GPU to do the transformation. And being a part of NVIDIA, I'm happy with that. So no corrections there. That's pretty much what I had in my mind. Thanks a lot.